In this experiment, we will be determining the heats of neutralization for two different acid-base reactions. The objective of this experiment is to determine the enthalpy of neutralization of hydrochloric acid and acetic acid with sodium hydroxide. We will use a coffee cup calorimeter to measure the heat flow for the reactions, once the heat capacity of the calorimeter has been measured. Most chemical reactions are accompanied by a change in the temperature of the reaction mixture. This temperature change occurs due to a change in the heat content, denoted Q. At constant pressure, we use the quantity called the enthalpy, denoted H, as a measure of the heat content. The change in heat content is delta H and has units of joules per mole. When the temperature increases for a reaction, this is because heat is being given off by the system. This is a reaction that we refer to as being exothermic. Since the heat is leaving the system, we treat delta H as negative. Therefore, when we see the word exothermic, this tells us that delta H is less than 0. When the temperature decreases for a reaction, this is because heat is being absorbed by the system. Such a reaction is called endothermic. Since heat is entering the system, delta H is now positive. Therefore, when we see the word endothermic, this tells us that delta H is greater than 0. The relationship between the heat flow and the temperature is given by the equation Q is equal to C times M times delta T. In this equation, C is a value known as the specific heat for the material. M is the mass of the material, and delta T is the measured change in temperature. The specific heat of a material is the amount of heat energy required to increase the temperature of 1 gram of the material by 1 Kelvin, or equivalently 1 degree Celsius. Once we calculate the heat flow for a process, we can find the enthalpy change by dividing the heat flow by N, the number of moles of material. Let's look at a specific example. We're going to calculate the enthalpy change for the cooling of a 150 gram block of iron from 100 degrees Celsius to 30 degrees Celsius. The information we may need is that the specific heat of iron is 0.450 joules per gram per degree Celsius, and its atomic mass is 55.85 grams per mole. First, we have to calculate delta T. Remember that this is always calculated as the final temperature minus the initial temperature. So that delta T is 30 degrees Celsius minus 100 degrees Celsius, which gives a value of negative 70 degrees Celsius. Now we can calculate the value of Q. This is just C times M times delta T. C is 0.450 joules per gram per degree Celsius. M is 150 grams, and delta T, as we saw, is negative 70 degrees Celsius. When we multiply these, we get a value for Q of negative 4.73 times 10 to the third joules. The next step in the calculation is finding the number of moles of iron. We do this by taking the mass of iron, 150 grams, and dividing by the atomic mass, 55.85 grams per mole. This results in 2.686 moles of iron. Finally, we can calculate delta H by taking the value of Q and dividing by N, or negative 4.73 times 10 to the third joules divided by 2.686 moles. This value is negative 1.76 times 10 to the 3 joules per mole, or equivalently negative 1.76 kilojoules per mole. The tool that we use to measure these heat flows is called a calorimeter. Calorimeters range in complexity from very complex to extremely simple, but they are all constructed in a very similar way. The sample must be isolated from the outside world in some way, with only a thermometer inserted into the calorimeter to measure the temperature changes. we will make use of the simplest type of calorimeter, known as a coffee cup calorimeter. This consists of two styrofoam coffee cups nested together with a cardboard lid over them. The lid has a small hole for a thermometer to be inserted. This is then placed inside of a beaker to make it more stable. Occasionally a stirrer is included, but we will not use this in this experiment. All calorimeters suffer from the same problem, and that is that the sample is always in contact with it. This means that part of the heat energy will always be absorbed by the calorimeter. As a consequence, the temperature change that we record will not tell us all of the information about the heat change in the system. This is because some of the energy is lost to the calorimeter. We have to account for this lost heat when we calculate our delta H value. Our heat flow now has two terms with it. The first, C times M times delta T, is the same term that we introduced in a previous slide. The second term, C cal times delta T, corrects for the heat flow absorbed by the calorimeter. C cal is called the heat capacity of the calorimeter, and it has units of joules per degree Celsius. We have to add these two contributions together to get our total heat flow amount due to a reaction. The first step of the experiment will be to determine the heat capacity of the calorimeter. We must have this value before we can determine the heats of neutralization. The second part of the experiment will involve neutralization. When an acid and a base are mixed, they will consume each other in a process known as neutralization. Strong acids and strong bases are named this because they completely dissociate in water. This means that neither of the acid or the base form still exists in water, but rather have completely dissociated into its component ions. For example, hydrochloric acid, when added to water, completely dissociates to form hydronium ion, H3O+, and chloride ion. Sodium hydroxide, a strong base, reacts with water to completely form sodium ions and hydroxide ions. The neutralization reaction for a strong acid-strong base mixture is the recombination of the hydronium ions with the hydroxide ions to form water. H3O plus OH minus, forming two water molecules. The delta H value for this, the heat of neutralization, is negative 57.2 kilojoules per mole. Note that this value is independent of the identity of the acid or base, provided that they are both strong. For example, if we neutralize nitric acid with lithium hydroxide, we will also obtain a value of delta H equal to negative 57.2 kilojoules per mole. When a weak acid is neutralized by a strong base, we obtain a different heat of neutralization. This is due to the fact that weak acids do not completely dissociate in water. A relatively large fraction of the acid stays in its original form when added to water. An example is acetic acid, CH3COOH. When added to water, it partially dissociates into the acetate ion, CH3COO- and hydronium ion. The extent of this dissociation is determined by the equilibrium constant for the reaction, Ka. As a consequence of this partial dissociation, the hydroxide ion now has two acids to neutralize, the hydronium ion and the undissociated acetic acid. The first reaction is the same as before, H3O plus OH forming two water molecules, and the delta H is the same, negative 57.2 kilojoules per mole. The second reaction sees the acetic acid reacting with hydroxide ion to form acetate ion and water. The delta H value for this reaction is positive. The overall heat of neutralization is now the sum of these two delta H values. As a result, the heat of neutralization will be a less negative number for a weak acid than for a strong acid. Additionally, the heat of neutralization will depend explicitly on which weak acid we are neutralizing, because each weak acid has its own different Ka value. Now let's take a look at the experiment. In part A, we are going to determine the heat capacity for the calorimeter. In this first part, we have to determine the heat capacity of the coffee cup calorimeter before we can perform the neutralization reactions. The way we do this is to use water at two different temperatures to calibrate the calorimeter. First, 50 milliliters of room temperature distilled water will be placed inside the calorimeter. An additional 50 milliliters of water will be heated until it's about 20 degrees Celsius warmer than the first. When these two masses of water are mixed inside the calorimeter, the final temperature of the 100 milliliters of water should now be between the cool water temperature and the hot water temperature. Since we have equal masses of water, we should expect that the final temperature should be exactly the midpoint between the hot water temperature and the cold water temperature. This is because the heat energy released by the hot water is completely absorbed by the cold water, and the resulting temperature should be the midpoint. What we will observe is a little bit different. In fact, the hot water will lose more heat energy than the cold water absorbs. As a result, the temperature of the hot water will decrease more than the temperature of the cold water increases. Now, according to the first law of thermodynamics, heat energy in a closed system can neither be created nor destroyed. And so this missing heat energy must go somewhere. It turns out that this difference is the heat lost to the calorimeter, which is related to the heat capacity of the calorimeter. We begin by recording the cold water temperature, which is 23.2 degrees Celsius. The hot water has been heating, and we add the thermometer to it. It will take a minute or so to get the final reading, and once the wire is moved, we will be able to see it. We now see that the final temperature of the hot water is 39.8 degrees Celsius, and we can mix them and attempt to put the lid on. The temperature change is actually fairly rapid, and we will see that it will stabilize very quickly. The final temperature of the mixed water is 31.3 degrees Celsius. Having completed part A, we now have the following data. The temperature of the cold water is 23.2 degrees Celsius. The temperature of the hot water was 39.8 degrees Celsius, and the final temperature was 31.3 degrees Celsius. Note that the midpoint between T hot and T cold should be 31.5 degrees Celsius, and we are slightly below this value, as expected. The calculations for this experiment are a little detailed, and so rather than focus on those right now, we will put this off until the next video. We're now ready to complete part B, the neutralization of hydrochloric acid with sodium hydroxide. Before we do anything else, we must first completely dry out the calorimeter. Any residual water will change the heat capacity of the calorimeter. First, we begin by adding 50 milliliters of 0.1 molar sodium hydroxide to the empty calorimeter, and we record the temperature of the base. Next, we then measure out 50 milliliters of 0.1 molar hydrochloric acid, but we do not add this to the calorimeter yet. We record the temperature of the acid once we have cleaned the thermometer well. If we do not clean the thermometer, the residual sodium hydroxide will partially neutralize the acid before we're ready for the experiment to begin. Note that the temperature of the acid must be within about 0.5 degrees Celsius of the base, otherwise our values will be incorrect. Next, we can then pour the acid into the base, give it a stir, and cover it. The final temperature of the mixture as it reacts should be higher than the initial temperatures of both compounds. Here we begin by measuring the temperature of the hydrochloric acid. It's 23.5 degrees. After wiping off the thermometer, I place it into the base and measure its temperature. The temperature of the base is found to be 23.2 degrees, which is within the 0.5 degrees Celsius limit. We now carefully pour in the acid and give it a stir and cap it. Notice that the temperature is increasing as the neutralization reaction occurs. We find that the final temperature of our neutralized mixture is 29.8 degrees Celsius. Now that part B is completed, we can look at the data. Again, the temperature for the sodium hydroxide was found to be 23.2 degrees Celsius. The temperature for the hydrochloric acid was 23.5 degrees Celsius, and the final temperature after reacting was 29.8 degrees Celsius. As before, we will wait until the next video to focus on calculations. The final part of this experiment is the neutralization of the acetic acid with sodium hydroxide. We first must wash and completely dry out the calorimeter. We don't want any residue from the previous run remaining in the calorimeter. As before, we begin by adding 50 milliliters of 0.1 molar sodium hydroxide to the empty calorimeter and record the temperature. Then we measure out 50 milliliters of 0.1 molar acetic acid, and again do not add this to the calorimeter until we're ready to begin the run. We record the temperature of the acid after cleaning the thermometer. As before, it must be within 0.5 degrees Celsius of the base. We can then mix the acid in the base, stir, and cover. Once again, the final temperature of the mixture should be higher than the initial temperatures of both compounds. We see that the initial temperature of the acetic acid is 23.7 degrees Celsius. Having cleaned the thermometer, it's now inserted into the sodium hydroxide. After equilibrating, we find the temperature of the sodium hydroxide to be 23.5 degrees Celsius. We're now ready to add the acetic acid to the sodium hydroxide and allow the reaction to occur. As before, the temperature increases quite rapidly as the reaction begins. As we allow the reaction mixture to equilibrate, we find that the final temperature is 29.8 degrees Celsius. The data for part C are given below. The temperature of the sodium hydroxide was 23.5 degrees Celsius. The temperature of the acetic acid was 23.7 degrees Celsius, and the final temperature was 29.8 degrees Celsius. It's important to note that even though the final temperature for this run was the same as the final temperature for the strong acid neutralization, our initial temperatures were slightly higher. This means that the overall change in temperature will be slightly smaller. This concludes the data collection for the heats of neutralization experiment. The calculations for this experiment are not difficult, but they must be done in the correct order. In the next video, we will go through these calculations step by step.